Well, so in my talk, what I'm going to tell you is about some results that we get when we, our main goal is to see how entanglement, which is the correlation that you observe between different quantum particles, propagate in quantum networks. So I think the audience here is quite diverse, so perhaps if I'm using I will try to keep everything at the basic level, but and you can stop me even for technical questions, because my technicalities, won't be, it will be, I've tried to keep it basic. So I guess if you make a technical question, it will be a basic technical question that I will be able to provide a basic technical answer. Okay. I don't know. Just stop it. Okay? And, just to say that, this is an old picture of my group. People move and they go. Several people here are not there now, but somehow most of the things I'm going to explain were done in collaboration with Danny Cavalcanti, who was a PhD student in my group, then a postdoc, and now he's in Singapore. Then with Sebastian Persegues, who was visiting us when we took this group picture, but actually he's a former PhD student of Ignacio Cirac, with Ignacio Cirac from MPQ, with Maciek Leszstein, who is another group leader at ICFO, and with John Lapere, who is working with Maciek and me at ICFO, and who is sitting there, and we'll give a talk tomorrow about some of the things I'm going to tell you about. Okay. So there were two things in my title. One of the aspects was quantum networks. So what is a quantum network? There are many possible definitions, but during my talk, a quantum network will basically be, say, a many particle quantum state. But I will think of this many particle quantum state as the result of a quantum communication network. Okay, so I will have this say complex structure. In the end, it won't be that complex, but in principle, I have all these nodes that have some quantum correlations, and all the quantum correlations are described by a quantum state rho. Okay, so this is the zero approximation to the concept of quantum network. And what happens in quantum information theory is that there are very standard scenarios that there are two distant parties, Alice and Bob, who are connected through this network, and they want to achieve a quantum information task. Okay, they want to say send private information using quantum cryptography. Okay, so one of the ways of doing that is if they establish what is called an entangled state between them. Okay, so they are able to have two quantum particles that have very good correlations. Okay. I can define these if you want with technical terms, but by this I mean that whenever I do something to this particle, the other particle is highly correlated to the result I got in that particle. Okay? So they want to establish very good quantum correlations at a distance. Okay, and they want to do that. Maybe with the help of the other nodes. Okay, so the other nodes can make some operations here, here, here. They can communicate classically, and at the end of this process, say through the network, these two distant nodes establish good quantum correlations. Okay? And during all my talk, I will assume somehow that there is a difference, an important difference between classical communication and quantum communication. Okay? So if I want to send you classical communication, this is today easy. Okay? I can send you many photon light bulbs and you will get it. Okay? If I want to send you quantum information, I have to send you very attenuated light bulbs. Okay, so I have to go on the photon level, and this is much harder. Okay, this is why I take classical communication among the nodes as a free resource. Okay, they can pick up the phone and communicate as freely as they want. Okay, so there is a difference between classical communication and quantum communication. You know what I'm going to say. So so the motivation is that these two distant particles, with the help of the other nodes in the network, get these strong quantum correlations to make a quantum information particle. So what's the solution to this problem? The standard solution was proposed in this paper by Briegel, Dulce, and Zoller, and it consists of the idea of the quantum repeater, okay? Which is somehow, it mimics the standard repeater that we have nowadays, okay? So you know that in classical communication, if you want to send a message from one location to another location which is very distant, well, you don't do it directly, okay? You send to an repeater, which takes this information and amplifies and sends and amplifies and sends and so on until you get the last node in the communication line. Okay? Well, this solution, the direct translation of this solution to the quantum regime is not possible because in the quantum regime there is no such a thing as amplification of quantum information. Okay, so this is something called the non-cloning theorem. But what this tells you is that you cannot amplify quantum information. So you have to do it in a different way. And the way these people found was what you have to do is you have somehow to make a repeater not with the direct information but with with quantum correlations. Okay? So what you do with the repeaters is not that you establish not direct communication between, say, the first node and the repeater, but you establish good quantum correlations between the first node and the repeater. And now this repeater establishes good quantum correlations with the second repeater, and the second repeater with the third, and so on, so on, so on, and until the very last step, the nth repeater establishes good quantum correlation with the nth repeater. Okay? And then what these guys do, once they have these good correlations, there is a process called entanglement swapping. In such a way that at this repeater you make an operation, and then the good correlations now are mapped from A, L1, and R2 to A and R2. Okay, so there is a process here that somehow establishes a solid line between these two properties. Okay, so you have these two links that have good correlations. You make an operation here, and then there is a direct connection. Okay? Well, I'm kind of explaining things in a high way. I mean, it's a qualitative argument. Okay, but you can make calculations. They are not that difficult. You can prove that this process works. Okay. So I'm going to enter the details of the construction, but it requires quantum memory. But it's technologically demanding. But at least it shows that there is a way of establishing this resource at very long distances. But I mean, if you see now, if you compare now the two pictures that I was showing, you see that there is some sort of here you see you have a very connected network, and here the solution I'm proposing you is a line. Okay? So you could think that, well, I mean, okay, this is good that we have a solution, but perhaps this is not the best you can think of. Okay? Because if you have a connected network, maybe you can think of something where you exploit the connectivity of the network, and you don't try to do it just following a line, but you really try to follow the fact that you have a connected network, so that the other parties can help in making these connections to the network. Okay? So our motivation was, I mean, is the quantum repeater idea all what we can do, or I mean, we can in some situations exploit the connectivity of the network. Okay? So that was our main motivation. I hope it's clear to anybody. Okay? Well, it happens that this question is complex, difficult. Okay? Why? Well, because I mean, unless I don't make any simplification, I mean, to find the best protocol in a sort of network where I can give you here a very complicated state is difficult. Okay? So what we did, we started by the first step, the most natural step, which is, let me just start by networks with regular geometries. I guess everybody will be happy with that. Okay, so I take, say, square lattices or triangular, hexagonal lattices, or just single lines. Okay, fine. And now what we do, experimentalists will kill me, but I'm a theorist, so I take the states pure. Okay, this is of course it's like a medical study, but I want to start the project, so I want to start by the simplest case. Okay, so what I do then is I design this network where I have these nodes. So now the nodes, you see, this is a node and this is another node. I'm very bad drawing even with a computer. Okay, but this node is supposed to be here. Okay, I mean this particle. Okay, so a node is given by this. Okay, so a central node has access to 4 quantum particles. Okay, and here you will have another node, here another node. And these nodes at the boundary, they have access to 2 quantum particles, and these 2 to 3 quantum particles. Okay? And this means that, so in my case, if I belong to the network, I'm connected with a pure state with Roberta, who in turn is connected with a pure state with Filippo, and we all share pure states in this very idealized world. Okay, so what I'm dealing with are these nodes. It's a many particle state, but actually this many particle state is composed just of quantum states of 2 particles, which are pure. Okay? In this case, the pure states of 2 quantum particles can be written in this form. I mean, this is called the Schmidt decomposition. Okay? So basically, it's just a way of an economical way of writing these connections. I mean, you don't have to care much about the details. Okay? There is a way of writing these states, and this is given. What it matters are these Schmidt coefficients that I can take in decreasing order. So these are positive numbers that somehow estimate the correlations that are present in this pure quantum state. Okay? So the first thing I want to show you is that although these networks are simple, they show some very rich, well, some reasonably rich structure. Okay. So let me just take the simplest example, okay, which is I now take the part. Oh, it's me. Okay, I'm sorry. I thought I checked. Okay, so let me just take the simplest example. Okay, you have now the particles have belong to a two-dimensional Hilbert space, so they are what is called qubits. And then the state of 2 qubits has this very simple form. Okay, you see, I mean, this is the state on Alice, and the other one is the state of Bob, so it can take two different values, 0 and 1. Okay, and I only changing the coefficients here. Okay, this. So now I'm back in the repeater configuration. I'm given a pure state between Alice and repeater, repeater and repeater, repeater and repeater, and last repeater and Bob. And I want these two particles to get a connected line by making some operations here. Okay. Well, this is a technical problem, not very difficult, that we can solve. Okay. Well, I mean, the solution is here. I mean, do you want to understand anything? Because I'm not defining anything. This, I think it doesn't make sense to explain it here. Okay, but it's something that we can define and we can solve. And actually, what we can prove is that in this particular case, there is an exponential decay of the entanglement that can be established here and here. So, for instance, one possible solution is that you apply entanglement swapping in these particles. Okay, so you make here an operation, here an operation, here an operation. But you can see that whatever you do, I mean, in the end, these two particles have established some quantum correlations, but the amount of quantum correlations decay exponentially with the length of the chain. Okay, so this seems to contradict the previous result of the quantum repeaters, but it does not, because in the quantum repeater scenario, you have many copies of the states. Okay, so I'm here considering a kind of toy model where I only give one copy between Alice and repeater, repeater and repeater, okay? While the repeater idea was defined for a many copy. Do you have a question? No?
See, but then it means that you need an exponential increase of the copies if you don't.
No. This is the nice thing about the repeater. That although although here there is an exponential decrease, yeah, you can compensate this without an exponential increase of the copies. Okay? So I'm not going against the quantum repeater. This is a very toy model where I give just one copy of a real state in my network. Okay? And in this situation, if I followed the repeater idea, I would have an exponential decrease of entanglement. That I'm not proving to you. Okay, you have to believe it, but it can be proven. Okay. So, I mean, what this means basically is that, okay, but there are some situations where I don't have, you see, well, this is a measure of an entanglement between the two end nodes. Okay? And you can see that this is the product of these determinants. And this is the matrix that is constructed with these coefficients. Okay? So basically, it's the product of these two numbers. Well, you can see that this number is always smaller than 1. This is why when you multiply all these numbers that are smaller than 1, you have an exponential decrease. Okay? There is only one situation where this is equal to 1, and this is the case where lambda 1 and lambda 2 are equal to 1 square root of 2. Okay? So this is 1 square root of 2. The determinant is the product of these two numbers, so it's 1/2. Multiplied by 2, you get a 1. Okay? So this is the only case where you don't get an exponential decrease. But this is the situation where you have here 1 square root of 2, 0, 0, plus 1 square root of 2, 1, 1. And this is the ideal situation where the state is maximally entangled. Okay? And then if the state is maximally entangled, you can really make an entanglement swapping. Okay? So, all this is to say that unless you have perfect quantum correlations between the node and the repeaters, there is an exponential decrease. Okay? As soon as you have some imperfections in the quantum correlations, even if they are at the pure state level, I mean, there might be some imperfections coming from the fact that these two numbers are not equal, then you have an exponential decrease between these two numbers. Okay, so now, this is what happens in the line. Okay, so here the repeater idea is bad. Okay, now let's see what we can do in the case of a connected network. So, and you will see that there is a link between this problem, which has a clear quantum information motivation, and something called percolation that possibly some of you know here. Okay, and the link comes from the following result. It is known in quantum information theory that if you give me a state which is not maximally entangled, I can always map it into a state which is maximally entangled. So maximally entangled state means that the correlations are good, are perfect. Okay, so if you give me a state which has not perfect quantum correlations, but is pure, I can always map it into a perfect quantum correlated state, but with some probability. And this probability is just a function of the coefficients I told you before, lambda 1 and lambda 2. Okay, I mean, it's not important, but there is a number, p, that tells you, Okay, you are given an imperfect pure state result, and you can map it into the perfect state result.
Sorry, what do you mean by mapping? Transforming by some...
Yeah, okay, sorry. So the set of operations is always, these nodes make operations on their labs, and they communicate the results. Yeah, by local operation and classical communication. And, okay, sorry. So whenever I say they apply some operations, I mean they apply local operations, and they communicate the result. Okay, so what happens then when you apply this? Well, this is a very known result. I mean, it was obtained in the 1980 or something like this. So let's see what happens when you apply this strategy to a network. Okay, so these two guys are connected by this imperfect pure state. Okay, in the sense that it's not perfect correlations, and they apply this majorization measurement. Okay, it's called majorization. Okay, and let's assume they are lucky. Well, good for them. Okay, so they establish perfect correlations. Okay. And they keep, I mean, now this node tries to do the same with this. He's unlucky. Okay, well, they failed. Okay, and now these guys try to do the same. They are lucky, and so on. Okay, so, I mean, for those of you, I mean, this is what's called a percolation problem. Okay, a percolation problem is something where you have a network of nodes, and with some probability you establish a connection, and with some probability you don't establish any connection. Okay, this is what you have here. And the good thing is that whenever you have established a connection by these red points, these correlations are perfect, and you can propagate them. Okay. So what we have now is that even if the connections were not perfect, were not red, okay, I'm still able to propagate entanglement via the network only because of the connectivity, while it was impossible in the line configuration. Okay, so what you have to do basically is we know how to compute this number given the entanglement coefficients. So I go to a book on okay, this process is called bond percolation because I mean it's defined for edges. Okay. So what you do, you go to a book on bond percolation, and they give you the threshold for the lattices. Okay, so there is a critical probability such that there is a connection among the two sides, between the two sides of the network. Okay, even in the asymptotic limit. So you go to the book, you open the corresponding page, and it tells you, the threshold is that, and you translate this into entanglement. Okay, into the amount of correlation that you need to propagate through the network. Okay. Well, so far it's good. It's relatively interesting. Okay, but it's somehow, I mean. We know that here we're dealing with quantum effects. I mean, do we have to go to a book on classical percolation to solve this problem? Okay, so maybe there is something better that we can do. So then we wonder whether, so we have some sort of process that is reminiscent of percolation, which is for quantum correlations, for entanglement. And in a way, it also defines a sort of phase transition. Okay, so there is a critical threshold probability such that you cannot percolate, and there is a critical probability such that you can percolate. Okay, so we hope that there is something like this. And the question now is to find this threshold, and clearly if you go to a book on percolation, you get the threshold classical, you can translate it into a threshold for entanglement. Well, now the question is whether this is all what we can do, okay? So whether this protocol is optimal. And the answer to this is no, okay? So it took us some time, but we found an example, which is not very natural, I must say, okay? But still, I mean, now we have better examples, okay? But this is the example we found. So it was a lattice, an hexagonal lattice, where the connections were given by actually two pure states. But still, I mean, you can prove that in this lattice you can tune the parameters such that the previous strategy does not work, and such that you make some other machinery in the network and you propagate entanglement. Okay? So I can give you the details if you are interested or the reference. Okay? But what I mean is that if you had applied the percolation book trick to this network, okay, you go to the book and you read the threshold and you see that it doesn't match with the entanglement you are putting in the network. Okay? But still, there is another way of doing things, okay, such that you can establish entanglement. Okay? So I know my explanation is quite qualitative, okay? But what I mean is that there is something new there, and there are new percolation thresholds when you try to propagate entanglement through a network.
Qualitatively, which is the new way? Just qualitative.
Do I have it here? It's very, I mean, the gap is small. Okay, but I will tell you more now about this, okay? So this is what we go together with Ignacio Firaki Maciek Levenstein, and somehow it shows that, well, there are some new thresholds to be computed if you are interested about the problem of entanglement percolation through networks with pure states. Okay? And now the question is that Roberta says whether this improvement over this classical threshold, whether we can wonder whether it's common and whether it's significant in a way. Okay? And for that, I mean, what we did, we introduced a new family of, I mean, we worked on that and we found a family of protocols that use multipartite entanglement. I'm not going to explain the details, but basically we tested several lattices And this is what was defined, say, by going to the book or to numerical simulations. And this is what our protocol was given. And you see the improvement, in some cases, was significant, like 20%. Okay. Well, this is just engineering, okay? But we tried our best, and up to now, this is the best we can get. Okay. And John is going to be more details about this. Okay, tomorrow. Okay, so that was nice, but what happens with mixed states? Okay. Well, the problem with mixed states is that we don't have any direct analogy with percolation, because you remember, I mean, my analogy with percolation came from the fact that I could transform my initial tropy into the ideal tropy with some probability, and this is no longer the case with mixed states. So I have to do some other tricks to propagate mixed states. Well, to be honest, there are some exotic rank 2 mixed states, such that this process happens with some probability. Okay, and then you can run all this percolation machinery for these states. But I mean, these are rank 2s, they are not full rank, okay? Which means that as soon as you add some natural nodes, they become full rank and you lose this effect.
They have a new paper from 2 months ago with rank 3 as well.
Yeah, but I mean, for me, if it's not full rank, I don't see any big difference with pure state. Okay, I mean, as soon as you add any natural noise, the not full rank property is lost. Okay, well, I mean, you can do something.
What do you mean by full rank?
So full rank means that there is no zero eigenvalues in your matrix. Okay?
In this case, it's 4x4 matrix. If you diagonalize it, there's no zero eigenvalues.
So if you go to the lab and you estimate a quantum state, it will never be less than full rank, okay? Because it's impossible that it has a zero eigenvalues. Remember, okay? As soon as you add some noise, you have some epsilon there. Of course, at the very same time, we are asking a lot to the project. I mean, to the problem. Okay, so this percolation effect is something that survives in the asymptotic limit. Okay, so maybe we don't want to have this. I mean, it's interesting from a theoretical point of view, but maybe it's not surprising that whenever you add noise, I mean, this result does not survive in some asymptotic limit. Okay? But more in general, for me, the problem of entanglement percolation is just the process of. I mean, I call it percolation because in our case we came from pure space and we had this connection with percolation, but I see it as a problem of distributed entanglement over networks. So it's interesting, for instance, recently Sebastian Sacegues has found an example of a cubic lattice. So it's not a square, but a cubic lattice with mixed states, and where he can find a protocol for percolation. I mean, it's a proof of principle result because, I mean, the amount of noise is very small, but it gives some hope for this kind of process. And we also find an example where you had this tree where we could also percolate. Okay? But I think it's quite artificial. Okay, anyway, so I think for mixed states, everything is open. Even the question whether you can percolate. But you can still make some connection with percolation. So imagine now that I go back to my initial scenario, this regular lattice, and now I give, instead of pure states, I give mixed states. Okay? Which is here. And now, possibly you know that for any mixed quantum state, there are many ways of decomposing this state. So if you give me a mixed quantum state, I can write it as the probabilistic mixture of states rho I. There are many decompositions that give the same state. Okay? So I don't know if you need this, but I mean, there are many ways of deriving a quantum state by mixing some other states. Okay? So now, among all these possible decompositions, you divide always the states here according to whether they are entangled or not. Okay, so whether they have quantum correlations or not. So whenever there is the state in this decomposition is entangled, you put it in this part, and whenever it's not entangled, whether it's called separables, you put it in this part. Okay, so for any decomposition, you can say, I put this into the separable part and the entangled part. And now you identify the decomposition such that the separable part is larger. Okay? Well, then you can prove that if this weight for the separable part, or actually the weight for the entanglement part, is below the threshold for percolation in this lattice, you cannot.
The classical or the quantum?
The classical. Okay? You cannot send entanglement in any possible way. Okay? So, I mean, again, I can give you more details about this, but I can make a connection between percolation. Okay? But although the connection goes in the opposite direction. So before, I was using the result of classical percolation to give you a protocol for entanglement distribution. Now I'm taking the classical percolation threshold to tell you that below this value it's impossible to make any process. Okay? So I don't know how much time do I have?
I need.
Okay. If you're interested, I can tell you later, okay? But what I mean is that I can still use techniques from percolation, but now in the negative side, okay? So if I'm able to solve this problem and I find something which is below the classical percolation threshold, I cannot propagate the current through my network. Okay, and the last thing I want to tell you is we also consider similar problems, but now in, well, I mean, we call, in the first version of the paper, we call the complex network, and one of the referees complained. But in my title, I still keep complex, okay? Well, I don't know. I mean, so because basically what, I mean, some other people have extended some of these results to complex networks, like the people in the Autónoma, Martín Cuquet and Joe Casamilla. They got, say, related results in this publication. And so what we did was we took the simplest example of a random graph. So now I don't have a regular geometry, but I have a random geometry. So this is the case where I have the nodes, and I can put a connection to the nodes with some probability. Okay, so this is an instance of my random graph where I put probability equal to 0.1. But here there is no notion of distance. Okay, it's not like in previous percolation stuff. So before I could put a bond only between neighboring nodes. Now there is no notion of distance. I start putting a connection with this, or 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 with this, with probability 0.1. Okay, so this is different than before. So here you have different instances for different probabilities. And this kind of networks with random properties, I mean, I'm not an expert on that, but I think they have found many applications in many different scenarios. Okay? So there is a property, whenever you take this first example of a random network, there have been some studies doing the following. So what you do, you give a probability for the connection that scales with the size of the lattice in a polynomial way, and you define the exponent of this polynomial z. Okay. So what I'm doing, I'm increasing the network, and at the same time, I'm decreasing the probability of getting a connection. Okay. And I'm doing that in this way. Okay. So this probability decreases with this exponent. And now I wonder, in the asymptotic limit, which kind of subgraphs appear in my lattice with probability 1. Okay. So I mean, this is a sort of asymptotics where you have to make the counting in the right way. Okay. But then you can prove that for z larger than 2, there is no connectivity. Okay, so the probability that you have a connection basically tends to 0. Okay, in the limit of large n. And this you can understand. Okay, so if z, so if you have a network, okay, so basically you are going to repeat the process of making a connection n times n minus 1 times. Okay, so you're going to try this with this, with this, with this, with this, then this with this, with this, with this, this with this, with this, okay? So in the limit, the number you try goes like this. So it goes like n squared, okay? Multiplied by the probability of getting an event, okay? This is what matters, okay? So if this exponent is larger than 2, this goes to 0, okay? And there is no connectivity in the network, okay? So this result is very clear, okay? That here there is no connection, I hope, okay? So more or less it was a quick explanation for that, okay? But then you can prove that for all these different exponents, you start having this subgraph with So what we did was, okay, let's try to do something similar, but now let's move to the quantum regime, okay? So now what I will do, I will replace probabilities by probability amplitudes, okay? So instead of giving, I will give pure states. Again, this is I admit it, I mean, a theoretical result, okay? But I give pure states to the networks and see what happens, okay? To the connections. So now I will do something like this, okay, which is quantum correlated, but I will send the quantum correlations to 0 with an exponent, okay? So I don't know why I moved, I could stay here, okay? So I send the quantum correlation to 0. If you see here, I mean, when n increases, this goes to 0, so lambda 1 is equal to 1, okay? And this, I get something which is not correlated, 0 for one node and 0 for another node. So this is what we define as the quantum analog of the previous process. But then interestingly, you see that the previous table collapses to z equal 2. Okay, so all the subgraphs appear for z equal 2. I mean, don't ask me about, I can show you the protocol, but I don't have any intuitive explanation for that. Okay, so there is, I mean, the whole table, of course, for finite subgraphs. Okay, I mean, there is a limit here where this doesn't happen, but for finite subgraph, you get all of them at a given exponent. Okay, and the last thing, I mean, what we are more recently doing is somehow combining the two approaches. Okay, so now I will consider the problem of entanglement distribution in a complex network. Okay, so this first result was more fundamental. Okay, let's take a result on classical quantum networks and try to do the same for quantum states and see what happens. And it happened that we got a surprising result. Now, what we are doing as well is, okay, let's try to see what happens when you consider a complex networks that probably is more realistic from an applied point of view, and see how entanglement can be distributed, even including noise. Okay, and this is something that John is going to explain tomorrow as well. So with this, I reached the conclusions. Okay. So it was fast and perhaps dense, but I hope I convince you that the distribution of entanglement through network defines a framework where you can apply some of these ideas from statistics, okay, like percolation. So somehow I think it would be nice to get more results on that. So I would say even for the pure states. So if perhaps you remember my explanation, I told you that you give me a network of pure states, I can give you a protocol where I make a link with classical percolation such that I distribute entanglement. Okay, so I give you positive results. I can distribute entanglement. However, I'm at the moment unable to prove you that for a very small amount of entanglement, I'm not able to percolate. Okay, so I know that when I have no connection, I cannot. Here, I know that I can, and in between, I don't know. I don't even know if a small amount of correlations are still able to propagate entanglement in the 2D. Okay? So I think it would be nice to prove that, okay, there is a region where even if you have some correlation, they are so small that you cannot send entanglement. Okay? This seems very plausible, but we don't have a proof of that. Okay? So for pure state, I think it would be interesting to understand if any amount of correlations is enough for percolation in the 2D systems. Okay? And for mixed states, it's rather the opposite. For me, it's relatively simple to argue that there is a region for noise such that I cannot distribute entanglement, but it's very hard to prove that in some region I can distribute entanglement over long distances. Okay, so it's complementary. And well, I think it also would be nice to extend this sort of results to other resources. I mean, I'm working on quantum information theory, so I care about how to distribute resources. So in particular, for instance, it would be nice to extend the result to secret keys. So now the nodes are connected, they have some secret keys, and they want to establish secret keys with a distant node. Okay? And also, I would say it's interesting to move this, say, very theoretical result to some realistic scenario where you consider finite networks, losses, and you put more dirty things in the network and see what happens. And also, I think for complex networks, I think everything is open there. There might be many interesting issues to discuss. And with this, I conclude with a list of references, but I think it's also, what I like also from this project that gives another approach. I mean, in the last year, there has been a very fruitful approach to many-body systems, in which techniques from quantum information theory were used to solve problems in these, say, many-body systems. And now somehow, in a way, we are reversing this. Okay, so I'm using techniques, say, from many-body stuff, okay, like this percolation, to solve a quantum information problem. And with this, I thank you very much.
Questions, comments?
Yes. I understand here that the goal is to establish a bipartite entanglement, right, between Alice and Bob. And the question is, will you gain some insights instead by using multipartite entangled state right from the start?
That is a very good question, and the answer is yes. I mean, I was very fast here, okay, but okay. What we did was, I mean, we took this case where we were starting with bipartite entanglement as well, but then we were immediately mapping into multipartite states. And this is the way we were getting these improvements. Okay, so yeah, as soon as you have a network, you can think of two things which are new compared to the in a way are. You have more possibilities in the sense that you have more connectivity. And this is what we use for the initial percolation result. But you can also think of establishing multi-party correlation. This was the missing ingredient in all what I said. But actually, we got some results also exploiting multi-party entanglement, and this is what John is going to explain tomorrow. Okay. So your intuition is correct.
I was wondering, you studied the problem of percolation of entanglement, let's say of spreading of the entanglement. imagine the other way around, that you have a network with a really many particle entangled state, and then small, I mean, it could be an ideal state, and then you add small noise and you check, or you want to calculate how fast the entanglement decays between A.
Okay.
I mean, would your study be somewhat related to this inverse problem? I don't know, is it clear for me?
Yeah, so, well, yes, let me see if I rephrase it and you tell me if it's correct. So you want to start from a given resource which is pure, no?
Yes.
Or good, a good resource, highly entangled state, and you want to start adding some, say, local noise at the particles and see how entanglement decays.
And of course, depending on the latest structure, it will decay fast or slow.
Yes. I mean, this is a problem which has been, I mean, I also have some papers on that, well, not only me, I mean, many other people. It's a very natural problem for quantum information theory because this is a very realistic scenario. Okay? Now, I don't think people have studied how the geometry affects this.
But on a network.
Yeah, I think, no, I don't think people have studied the way geometry affects this decay. Okay? I think people have studied how, let's say, you take particles in a line, and now you see how the entanglement decay, how it changes with the size. These people have done it, okay? But whether it decays faster in lattice, in square, or hexagonal, or things like, or as a function of connectivity, I'm not aware of any result.
Yes, I have two questions. One is, in both pure and state case schemes, you have the same state for all the leads, right?
In my case, I had the same state.
In both cases of pure and the mixed state.
Yes.
So what happens if you have a distribution? Like, okay, suppose you have a pure state, so lambda 1, 0, 0, lambda 2, 1, 1, and then you have some distribution around lambda 1. So you have some really small distribution around this value. What happens? How robust are the results? Or
Okay, so
if you are both threshold, can you go below threshold?
so if you in the scenario you are thinking of, you know which state you are given, although it happens with some probability, or you don't know which state you are given. Because if you know the state, then it's a mixed state.
No, okay, we know a state. Is it
You know the state?
Yeah.
I don't know.
But they're not all the same.
Yeah, I don't know.
They change a bit each
I
other.
don't-
But you know the same, so it's pure state.
Yeah, I don't know. Well, no, I don't know.
And the second question is,
Well, let me just, maybe I said, okay, if you don't mind. Actually, this is what we are using here, okay? So, why we know that here I cannot percolate, okay? Because in principle, I'm given a mixed state. But now I'm taking an even better scenario where I'm given rho S with probability PS and rho E with probability PE. And I know which state I'm given, which is not the same as having rho, it's a better situation, okay? So if in this scenario the PE is smaller than the classical threshold, then I won't be able to percolate even if I knew if I'm given rho S and rho E, so clearly I won't be able to do it with rho.
What do you know and not know here? Could you explain that again? That's just how do you know how to do that separation?
No, so maybe I have to do that, okay. So why we got this result on the impossibility for any protocol? Because here we were considering a network of mixed states, okay? So we were relaxing this scenario, somehow like what you were asking, okay? This is the only example I know along the lines that you said, okay? So instead of considering the state rho, I'm considering another scenario where the parties receive either rho S with probability PS and rho E with probability PE, okay? So they have a probabilistic mixture, but they know which state they are given.
They do.
Yes. This is not as having a mixed state, okay?
Yeah.
Of course, they can map it to a mixed state if they forget which state they are given, but they don't have to. I mean, this is very bad for them, okay? But clearly, in this situation, if you give them either an entangled state or a non-entangled state with probability PS, and the probability that you give an entangled state is below the threshold, there won't be any way they can make it. I mean, there's not even a connection of entangled states, okay? And this is why I know that if I'm below the classical threshold, there is no protocol in this situation which is better than the initial situation where they have a mixed state.
But if it was actually an unknown mixed state, it would be even worse.
Yeah, exactly. So, clearly,
And the same question, is it possible to generalize these protocols to higher dimensional systems like qubits?
yeah, but I
And,
mean,
and in case also to bosonic systems, like Gaussian states, and to make Gaussian distillation and so on?
Okay, I mean, I must say all these calculations, stuff. I mean, the zero protocol is very nice, but it crucially relies on the fact that you have this majorization result that you can perform with some probability. And these, as you know, for Gaussian states, we don't have. Okay?
So, only question for people not participating in the workshop, so then we can convene upstairs.
Your last transparency, you make you talk about the quantum many-body systems. All of this looks, the propagation entanglement looks to me like the long-range order in quantum many-body systems at zero temperature. Is there any relationship between having entanglement or not to quantum phase transitions at zero temperature? Is there any study of that?
Well, I mean, in a way, it is the same, but I mean, it is connected. But here, I'm demanding less. Okay, so because in the I mean, something what
it's because the type of communication between nodes.
Exactly. Because I'm allowing the part. I mean, in the many-body scenario, usually what you do,
they interact with some Hamiltonian.
Yeah, but what you do, you have a Hamiltonian, you compute the ground state, and then from the ground state, for instance, you see how this particle is correlated to this particle when they are distant apart in the thermodynamic limit. Okay, so what you do, you compute the two correlation point and function. Okay, 2-point correlation function between these 2 points. Okay, so somehow you are forgetting these nodes. Okay, while in my case, these nodes help in an active way the other ones by making operations and communicating the results. Okay? So there is a link, but it's not one-to-one, let's say. Actually, what I'm using is something called localizable entanglement. So they have this initial state, and all these nodes try to put as much entanglement as possible between A and B by making an operation and communicating the result. Okay? So I'm more, I allow them to make more operations than in a many-body system.
In your last, the one before the last transparency, you said that in terms of complex networks, everything is essentially open. But any hint on the role of hubs in these networks?
What?
Is there any hint on the role of the hubs of the networks?
Well, we made some studies on that, no?
Yeah, we started to look at that. That happens. You're talking about sort of. You're thinking of like a quantum internet or something like that.
Well, I'm thinking of a scale-free network.
Yeah, we get.
Oh, yeah, okay. Well, scale-free networks. Yeah, we looked at that yet, but we haven't published anything. But like, if
that's why I'm asking for hints.
Yeah. No, I mean you could ask for what's the difference between putting noise or affecting nodes of different degrees, putting degree distributions or something, or like how, and there's different reasons for looking at that too, classically as well. Because there's always link failures at a low level that happens with a certain amount, and then for attacks and so forth, this happens at times. But we don't have much to say at this point.
I mean, we didn't find any natural framework or any general result on that. I mean, natural framework, yes, but I would say we didn't find any general result.
No.
Well, first we could make some.
But I still think it's something to be looked at and should be looked at because
it makes sense.
There's going to be more networks of that type.
Question from people not taking part of the workshop? No. If not, send the speakers again. We have copies.